Nuclear binding energy is traditionally calculated using four primary coefficients: volume, surface tension, Coulomb forces, and asymmetry. These values are empirical fits, constants extracted from experimental data rather than derived from a foundational theory. Because these constants are tuned to match physical observations, the Standard Model operates as a description of behavior rather than a first principles derivation. A 2026 paper by physicist Georgiades Menelaos addresses this limitation through the framework of elastic continuum theory. Under this framework, atomic nuclei are defined as stable, topological supernauts formed within a continuous, solid elastic medium. This chart plots binding energy per nucleon against atomic number. We are going to reconstruct this distribution of nuclear stability from scratch. We will achieve this mapping without relying on empirical parameters, using the mechanical elasticity of the vacuum to chart both the known elements and the super-heavy frontier. By deriving these coefficients from the vacuum's mechanics, the model establishes a mechanical foundation for nuclear stability. To model a nucleus within this theory, we start with a medium that acts as an elastic, continuous solid grid. A nucleon manifests in this medium as a localized topological distortion. It is a superknot holding physical tension within the lattice. This continuum is governed by two baseline mechanical properties: the bulk modulus, represented by K, and the shear modulus, represented by the Greek letter mu. The bulk modulus dictates the medium's resistance to uniform compression, while the shear modulus dictates its resistance to twisting or shearing forces. The stability of any superknot is defined by this equation, representing the total energy density functional. It balances harmonic strain terms against higher-order interactions. The harmonic section incorporates the green Lagrange strain tensor, labeled E, and the chiral orientation field, labeled U of R. The final variables represent nonlinear stabilization terms, anchored by the lattice coupling constant, lambda. Without these nonlinear terms resisting the inward pull, the topological soliton would mathematically collapse under its own internal tension. The existence of stable matter is a mechanical equilibrium, holding the topological necessity of the knot against the continuum's elastic resistance. To calculate the energetic ground state of a specific atomic mass, we must subject this energy functional to the calculus of variations. By applying a symmetric hedgehog ansatz to the field, the Euler-Lagrange equations yield a second-order nonlinear differential equation governing the soliton's profile. Solving this is complex, driven by the presence of nonlinear sign components and squared derivatives. We constrain the equation using physical boundary conditions. The profile function f of 0 must equal pi at the core, and f of infinity must equal 0. This forces a regular core structure with a unit baryon number at the center, while ensuring mechanical strain vanishes at infinite distance. We execute high-precision numerical shooting methods to identify the exact spatial profile that satisfies both boundaries. A nucleus achieves a stable configuration as a mathematical inevitability, forced into shape by the topological boundaries of the elastic continuum. With the spatial profile solved, we can integrate the energy density over the soliton to extract the macroscopic binding energy coefficients. In equation 6, we extract the volume coefficient. The calculation relies on the bulk modulus, K. The volume term represents the energy required for bulk compression within the soliton core. Moving outward from the center, we evaluate the outer boundary of the knot. Equation 7 derives the surface correction, where the calculation shifts to the shear modulus, mu. Surface tension is dictated by the continuum shear modulus and the lattice cutoff radius at the boundary. We also extract the topological asymmetry penalty, which similarly relies on the shear modulus, mu. When proton and neutron distributions diverge, the resulting internal shear stress produces the energetic penalty. The parameters of macroscopic nuclear physics are expressed here as direct functions of the vacuum space elasticity. We now feed the concrete continuum moduli values, 230 mega-electron volts for bulk and 100 for shear, into an iterative numerical scan across the elements. For every atomic number Z, the algorithm tests varying neutron numbers to identify the combination that minimizes continuum stress and maximizes binding energy per nucleon. This chart displays the output of the computational sweep, mapping the optimal stability states of the lattice. the algorithm reconstructs the established binding energy curve, aligning with known elements 1 through 118. At atomic number 26, the curve reaches its apex at iron. This stability peak occurs at the precise point where internal shear stress is minimized within the lattice. Because the model is derived from mechanical moduli, it can calculate the integrity of structures we have not yet synthesized. The scan pushes into super-heavy elements, identifying the structural tolerance limits of the elastic lattice before the plenum reaches instability. The periodic table acts as a map of the continuum's mechanical limits, charting where the elastic plenum maintains stability and reaches its breaking point.